Section 6.2, and here we're looking at an application of diagonalization. So powers of A when I can write A equal when I can write when P inverse AP equals D, D is diagonal. Okay, so if that's the case, then we have that A is equal to, well, multiply on the left by P, and so we'll get P times D, and multiply on the right by P inverse, and we'll get P inverse over here. So we have that, and so notice then that, you know, A squared, and I think we've already done this induction proof, right? A squared is PD P inverse times PD P inverse, and that is P D squared P inverse. And so in general, AN is P D to the N P inverse. So if we know P, D, and then P inverse, this computationally, this is pretty darn simple compared to actually multiplying out A to the N. And again, that induction proof would be, you know, something like, you know, A to the N is A times A to the N minus 1, which means that that's P D P inverse times, using our induction hypothesis, P inverse D to the N minus 1 P, and that gives us our P D to the N P, I gotta change my inverse here. Maybe, there we go. P inverse, like so. Okay, so that was our induction proof. And so, you know, if I have some matrix, and let me see, they gave us in example 6.22, they gave us a case where, you know, A is equal to 2, 1, 1, 2, and P is equal to negative 1, 1, 1, and 1. So my eigenvectors are negative 1 and 1, and then 1, 1. And D, corresponding eigenvalues, were 1, 0, and 0, were 1 and 3. And so this means, you know, that, for instance, A squared should be P D squared P inverse. So we need, you know, we'll need P inverse here in a minute, but let's see. So let's look at A squared and actually do that. And that's 2, 1, 1, 2 times 2, 1, 1, 2. And so we get 4 plus 1 is 5. 2 plus 2 is 4. 2 plus 2 is 4. And 1 plus 4 is 5. Interesting. Okay. Now we need P inverse. So P is minus 1, 1, 1, 1 So what the heck's P inverse? I don't know, probably my easiest way to do that would be to just start with minus 1, 1, 1, 1. I could do the, well, yeah, we'll do the determinant thing. And so we need to swap. So P inverse is equal to, we'll do 1 over the determinant. So the determinant here is -2. And then times swapping the diagonal elements here, and then, whoops, and doing the negatives of these, I think. I always have to think about that formula, but I think that's right. Let's see, did we get that right? Yeah, we got that right. So that's P inverse, so that's minus 1/2, 1/2, 1/2, 1/2. Okay, and if we check that out, it does indeed give us the identity when we multiply P inverse times P. Okay, so we have that for A squared. Now let's try P times D squared times P inverse. And so that is equal to our minus 1, 1, 1, 1 times 1 squared, 0, 0, 3 squared times minus 1/2, 1/2, 1/2, 1/2. And so this is equal to, well, I'll get 1 and 9 in there on those diagonals, so I'll get minus 1 times 1, so I'll get minus 1, and then 1 times 9, I'll get 9, 1, and 9, like that, all times minus 1/2, 1/2, 1/2, and 1/2. And so now I get plus 1/2, and then plus 9 halves, that's 10 halves. So I get 10 halves, which is 5. Then I'll get 8 halves here, which is 4. And minus 8, yeah, 8 halves. And 10 halves. And so that is indeed our 5, 4, 4, 5. Okay, and we could do it for larger powers on A and D, but I think that kind of gets that idea across. Okay, and so that's one application.